Hello everyone, this is Dr.Hira here. So as we are discussing about the reactions of the carbonyl compounds, and in my previous lectures, we discussed about different reactions of the aldehydes and ketones. And today we will focus on two of the very important reactions. Basically, the chemistry is the reduction. So these are the reduction reactions, but they are the two very famous named reaction which need to focus. And if you are discussing the carbonyl chemistry, so that's not complete if you don't know about the Clemmensen and wolff-kishner reduction reactions. So just a reference of the previous lecture, and I have shared the link also, which I will add it in the description of my YouTube lecture, so you can watch if you want to review the other reactions which we have discussed so far. So we have discussed the different oxidation reactions, some of the other important reactions of the carbonyl compounds with the metal hydrides, and we see that the carbonyl compounds can be reduced uh, and they can give you the alcohol as a product, and they can give you the alkanes. So today we will discuss about when the reduction of the carbonyl compound is giving you the alkanes. So what we discussed in a previous lecture is that this carbonyl compound can be reduced in the terms that we are getting the alcohol out of this ketone or aldehyde. But if we this carbonyl compound converted into the methylene, so this is giving you the alkane as a product class. So firstly, we will discuss the reduction of the carbonyl to methylene, and we from this you came to know that in this particular topic, either we though we are discussing these two important reactions, one is the Clemmensen reduction and the other one is the wolff-kishner reduction. So this reduction will result that this carbonyl group, which is a C double bonded, is converted into the CH2 methylene group, and this carbonyl, either aldehyde or ketone, will give us the alkene as a product. But firstly, we have to compare these two uh, reduction reactions and what is the significant difference and how they are different. So though the product is the same, the end product is the same, that is alkane, but there are some of the limitation, specificities, and the medium which we are using for conducting that reaction. So firstly, just look at Clemmensen reduction. So this was developed by German chemist E. Clemmensen in 1912, and the reduction of the carbonyl group of an aldehyde or ketone to a CH2 group using zinc amalgam and concentrated acid, which is the HCl. This is the hydrochloric acid. So this zinc amalgam is basically the zinc metal, which is deposited at the surface. We are using the mercury for its surface for making that amalgam. So basically the catalyst or which is reacting is the zinc metal, but the amalgam or the mercury is making a useful form of it, and this is deposited on the surface of the mercury. The Clemmensen reduction requires the use of concentrated HCl. So it means that reaction is rich in protons. So we have the hydrogen or H positive ions and the protonation medium in our reaction system. So it cannot be used to reduce a carbonyl group in a molecule that also contain acid sensitive groups. So you have to think about, so you have to work on that what is your reactant material and what should be your suitable reduction method. So either you have to go for the Clemmensen reduction or either you have to wolff-kishner reduction. So for the Clemmensen reduction, you are limited that you can't use that kind of carbonyl compound which have another substitution, which have another group, or the solvent system, which has the sides that it can undergo the dehydration or an acetyl that it hydrolyzes so that its resulting carbonyl group is also reduced. So there shouldn't be such species that which can be reduced by taking this H positive ion from the Cl, because now this HCl is also working for the hydration of this carbonyl one. So we will see in a mechanism that how that works. So the third difference is that aprotic solvents are suitable. If we use the protic solvents, so they react vigorously, and obviously they are able to react with the HCl, so that is not suitable for the Clemmensen reduction, and because we can't target our reactant carbonyl compound. The second one is the wolff-kishner reduction, and this was discovered independently by two scientists. One was the Kishner and Kishner, who was working in 1911 on these methods and on the reduction of carbonyl compounds. And the other one was L. Wolff in 1912. So they all, three scientists were working almost in the same years on the carbonyl compound reduction, or the reduction of the C double bond O into the CH2. Or this method was because they are using the same medium and reaction conditions. So the both name were combined, and that's why this reaction is famous with the wolff-kishner reduction. So the basically what is that wolff-kishner reduction is? So this is the reduction of the carbonyl group of an aldehyde or ketone to a CH2, and that point is same with the Clemmensen reduction, but using hydrogen, which is the NH2NH2, and a base. Now we are using the basic medium, and we are using this nucleophile, which is nitrogen nucleophile. This is NH2 and NH2. In this reduction, a mixture of the aldehyde or ketone, hydrazine, and concentrated potassium hydroxide, which we will use as a base, is heated at a flux in a high boiling solvent, such as diethylene glycol. So that is the solvent we will use. But in case of the Clemmensen reduction, we can use some of the solvents which can be useful for simple ether. We can use, or the usually this happen in the ether or the methyl medium even. So but the tertiary alcohols can't be used because they have the very stable carbonyl intermediate, and that can be easily reduced with the presence of this HCl. So the product solvents are suitable in case of the wolff-kishner reduction, but we usually use the very high boiling diethylene glycol, right? So it is a product solvent, but it is high boiling because we have to give the more time for this reaction to conduct and the reduction of this carbonyl one. Now we will see one by one the mechanism and how these reactants and the reagent, the reducing agents are attacking on the carbonyl one, and we are getting our desired products. So the first one is the Clemmensen reduction. So here you see this is the one of the alcohol, one of the ketone. So this is the 1,2-hydroxyphenyl hexane 1-one, right? And this is the HCl which we are using. There is the zinc amalgam which we are using as a reducing agent, and we are getting the product, this carbonyl species, right? This is reducing in the CH2. Now this oxygen has removed, and this carbon get two hydrogens from these reagents, and then it is converted into the methylene. When this is a CH2 and it is bonded from the both sides, we call this methylene, right? And don't confuse it with the the bonds, which is called methine, right? This is the methylene, right? So that is a species. It is converting, or overall, what is a class of compound that this ketone is converting into the hydroxy alcohol. So that is another substitution. So we are not discussing that one. We have seen that these are the reactions which particularly work on only the target only on the carbonyl group, right? So this carbonyl will convert it into this one. And if we just ignore the substitution, so this ketone or aldehyde is converting into the alkane one. So the rest of the substitutions will remain same. So there was a hydroxy on the phenyl ring, and again we get that hydroxy here, right? So now the major function group in this product is the hydroxy one. So that's why we named it as the 2-hexyl phenol. Now we will see the mechanism, how that works. So this is our reactant compound. I have condensed this molecule for the convenience that this CH2 I have add the brackets with the 4 number, that they are the 4 carbon CH2, and then this is a CH3, right? So this was basically the 5-membered chain next to the carbonyl one. So now this is a zinc, and why I have put it this black bar, this is to show that this is on the mercury surface. So this is a zinc amalgam, and we know that zinc is the +2 electropositive, and it has the potential to donate the 2 electrons. So now we will see how that works and how we are getting our product. So firstly, when the zinc amalgam is interacting with this carbonyl, the first interaction is between the zinc and this carbonyl group. So this is somehow similar, but this is now the uh, this is basically the heterocleavage. This is not the homocleavage. This is a homolytic cleavage where there is the 1 electron movement, right? So this is not that the whole 2 electrons or the pair of electrons will move there. So this is through the homolytic cleavage. Homolytic means that the one electron is shared with the 2 atoms which were making initially the bond. So this is oxygen and a carbon. So now when they are cleaving through the homolytic, so 1 electron will get back to the carbon and 1 electron is going back to the oxygen. So now you can see there. So this is the 1 electron. Sorry, we just have to go ignore this electron extra. There is hypos mystic. So this is only the 1 electron, and 1 electron is uh, has gone back to the oxygen, and 1 electron is contributing to the zinc. So they have established a bond there, right? So now this oxygen has make a bond, one with the carbon, one with the zinc one. So now we will see that what is the next, okay? So here, this is the intermediate, and this is the member or 3-member ring, which initially developed here to stabilize this one, because in that form, this is not stable. So there was a 1 electron, there was 1 electron. So they also had to establish a 1 bond with each other. So now there will be the removal of the water. And here, this is the minus H2O, and we know we are using the acidic medium, so there is the proton available in that system. So here the hydrogen ions are taking up that oxygen from this one, and this bond will break. This bond will go back to the oxygen, so that will remove with the 2 hydrogen ions, and here zinc will establish the 2 double bonds with the carbon. So the next is that there is the HCl still in a system, because we are using this as a medium, as a second reagent. So we have added it. So this is not only the single molecule, there are a number of HCl molecules that are present in this reaction medium. So now the chlorine and HCl, this is the polar molecule, polar bond, and now this zinc is giving its electron pair to the hydrogen. It is capturing that proton, and this chlorine will take back its electron. And because we know the halogen are highly electronegative, and these alkali metals or the transition metals, so which are on the left side of the periodic table, they are more electropositive one. So now this zinc can combine with the Cl on a later state, right? So there will be the zinc chloride which will be removed from this, and here there is a one proton which has attached to that system. Now again there is another HCl molecule which will combine with this, and it will take back this zinc, right? So this zinc chloride is basically produced which has attached this. So I will just write it here to mention it, that from the interaction of this HCl and the zinc chloride has produced. So this is not liberated at the moment, because firstly it has to be in its complete and the stable form, which is a zinc chloride, ZnCl2. So now one other molecule of the HCl is combining or attacking, and this bond will break, because now this carbon is the electrophilic, right? And when this is this bond will attack on this H, so this electron pair will be on the carbon, and this is making this carbon a carbon anion, no more the electrophilic one, right? So now this zinc chloride will be removed with the Cl, and this hydrogen will be captured with that carbon, and now we have the CH2, CH and CH, and overall we have the zinc chloride and the water molecule as a byproduct. So this is the mechanism of the Clemmensen reduction. So the one electron, the first interaction is basically from the zinc. So then they establish, and this was the intermediate where there is a zinc based molecule which has formed by the reaction of the zinc amalgam in the presence of the HCl. And then there is the another basically the intermolecular rearrangement, that we have HCl, and overall we then get reduce that carbon with H and H, two hydrogens is added to that molecule. Now the next one is the wolff-kishner reduction. So in case of the wolff-kishner reduction, we are using hydrogen and the basic medium, and the diethylene glycol, which is the high boiling liquid, and this is the product solvent we are using here. So overall product will be again the alkane, because this carbonyl is converting into the CH2, and in the byproduct we will get the N2 and H2. So one thing about the wolff-kishner reduction, that it is more lengthy in terms of its mechanistic steps. Second thing is the use of the high boiling solvent, though this is perfectly fine. We are using a number of these different synthetic reactions, but sometimes this is harder to work up the reaction. So how you can remove that high boiling solvent system from the medium. So now we will see the mechanism of this one. So because just to keep it a little bit understandable, so I am just not mentioning these steps, but if you are interested to cover these mechanism steps also, so you can just check out the reaction of the aldehydes and ketones with the N-based nucleophile, nitrogen-based nucleophile. So you will see how the ketone and aldehyde can form the hydrogen. So basically, because this is the sometimes you are familiar with that reactions, and we do in some of our lab assignments and in our experiments also that we do convert the carbohydrates into the hydrogens by the reaction with the phenyl hydrogen and the hydrogen one. So I'm strictly starting with the hydrogen formation, but if you still want it and you are interested, that you can explore that step also. So you can check out any organic chemistry book and you will see the mechanism how the ketone can convert into the hydrogen. And basically these steps were very much important, and they are hard to find normally, and all kind of resources. So I've worked hard on it. So that's why I'm sharing and I'm discussing this mechanism with you, so that you will commonly get the hydrogen formation mechanism. So firstly, we are starting this example of one example for the wolff-kishner reduction from the ketone. So this is a ketone, and this is the acetophenone, the molecule name is, and the hydrogen is there. So the first step is that there will be the hydrazone formation, and hydrazone is a compound where the N is doubly bonded with the carbon. So this commonly we known as the hydrazone. So as we are using the basic medium, and for the base medium we are using the potassium hydroxide, which is very good and a highly basic agent. So what is happening here that this OH is very strong, and it can capture the proton from one of this amino site NH2, and here you will get this intermediate C double bonded N, and then there is the NH with the one negative because there is the one hydrogen which has removed, and it's having the two electron pairs on nitrogens. So this is still deficient with the one more bond, because it can make maximum 3 bonds to complete its octet one. So now the next step is that in the system where there is the water medium, because we are using this potassium hydroxide and that solution we have used in the reaction system. So what is happening here, that the HOH will attack on it, and there will be the protonation of the carbonyl carbon ketoenol tautomerism. So that is the ketoenol formation. If you just look at the previous step, so to until it is getting another atom to make the third bond, so there is internal adjustment that this electron pairing is establishing the double bond with this nitrogen, and of course then this electron will go back to this one. So why this is happening, we have talked about the stable carbonyl and the carbocation. So now if you just look at, this is a secondary one. So this secondary intermediate is more stable as compared to this is at the terminal position. So this arrangement can easily be done. So now this is the carbon anion which has formed, and when it approach with the water molecule, so there is a protonation of the carbonyl carbon, and this protonation results as CH, there is a CH3 and double bond NH, and this is the electron having the electron pair. Both of nitrogen have the 1 electron pair. So now in our system we have that basic solution. So again, this is capturing this proton of this hydrogen or amine nitrogen. So now we will get, and this intermediate is called the 1-phenylethyl diazine. Diazine means aza is for the nitrogen. So there are the different rules for naming the heterocompounds. So di is for the 2 and aza is for the nitrogen, and ene is to showing it that they are connected to the double bond. So now there is a OH which will attack and capture that proton. So this hydrogen is removed from the nitrogen. And here there is internal adjustment again. So this electron pair will establish a triple bond, and this bond will broken, right? So there was the water molecule which was formed, by the reaction of this OH and capturing this proton. So now, as this N, when it makes a 3 bond with each other, these are stable. So there is no need of that nitrogen to make a bond with the carbon. So that bond will broken, and this carbon is um, leaving this nitrogen to live his own life with another nitrogen is a nitrogen gas. So this N triple bond N is basically N2 or a nitrogen gas. So here we're left with the carbon anion, and now the water molecule is there. So that carbon anion will attack on this water molecule, and it can capture either for the water molecule in place of the water molecule you can mention H, um, because through the water, but actually we are not using the acidic medium, so this is the more appropriate that you write the water molecule, because if you just write H positive, so it is giving the hint that you are using the acidic medium. But right now we are discussing the wolff-kishner method, which is a basic aqueous solution of the potassium hydroxide, and the solvent we are using is the diethylene glycol. This is for uh, facilitating the reflex reaction for the higher temperature. So now this hydrogen will be captured by this carbon, and there is a CH2, which is the methylene, and this is a CH3, and the rest is the OH negative, right? And this is the hydroxyl which has removed, which was strictly coming from the first one. So now this is generic formula of the product, that you will get whatever the R groups are attached to this carbon and carbon, so that has converted into the CH2. So more specifically this alkane, so you can name that alkane, starting from the ketone, we converted the carbonate into the methylene, and we get that alkane, right? So that is the mechanism of the wolff-kishner reduction. So now, at the end of the lecture, I have a task for you. So as we have covered the metal hydride reductions, which we discussed, lithium aluminum hydride, sodium boron hydride, then N2H4 is basically the hydrogen KOH basic solution. Um, yeah, we discussed today. Zinc, amalgam, and HCl we discussed today, and this is basically the Clemmensen reduction. We also talk about the alcohols and the HCl, right? So, and the chromic acid reaction of the aldehydes and ketone. So here, this is a table, and the task is that you have to draw the structure formula for the product formed by treating butanol with each reagent. So you just work on it and submit as soon as possible for my students. But the viewers or the people who are attending this lecture, and they are not students, but they have some queries, so you can just comment on just below the lecture video. So I will be very happy to answer your queries, and we can discuss that. Thank you so much. Have a good day.